Hi, my name is Yossi Gottlieb. I'm a Chief Architect at Redis Labs, and this is going to be a very quick introduction to RedisRaft. So first, what is Raft? Raft is a consensus-based algorithm for replicated state machines. So it means that it's an algorithm that makes it possible for a distributed set of processes to agree on some common state and operations performed on this state. Many people find Raft to be easier to understand and simpler than other consensus algorithms like Paxos. And because of this, we've seen a lot of implementations of Raft showing up in recent years. Some of these implementations have ended up being extremely popular and widely used systems like etcd, which amongst other things powers the control plane of practically all Kubernetes clusters out there. RedisRaft aims to bring Redis and Raft together and make it possible to create strongly consistent and fault-tolerant clusters of Redis servers. Now, we know that strong consistency is not free, and we have to trade performance and availability for it. And when we think of Redis, we think of performance, because traditionally that's what it was used for, and this is where it shines. But we also see more and more use cases where Redis is used beyond cache, and for those and others, we think that having more consistency options makes a lot of sense. So RedisRaft is implemented as a Redis module. It means that it's not a fork of Redis, or it doesn't require any changes in Redis itself. Instead, it's a module that can be loaded into existing servers, and once loaded, it provides its own alternative mechanisms for cluster leader election, replication of data, and persistence. Everything else is still Redis, so you get the same configuration interfaces, client support, data types, and commands. Other than this, RedisRaft provides everything you'd expect from such a cluster. So you can dynamically configure the cluster and have new nodes added or existing nodes removed on the fly in a safe and consistent way. You have the ability to perform log compaction, so Raft logs don't grow infinitely and take up all disk space or take forever to transfer on the network. You have an optional proxy mode, so clients can either be redirected towards the leader node or have the requests automatically be forwarded there. And it's quite configurable, so there's a lot of control over the performance versus consistency trade-off, and you can disable certain things like quorum reads or syncing to disk to get better performance if you're willing to sacrifice some consistency in some cases. So RedisRaft started off as an experiment at aiming at extending the Redis module API. Originally, Redis module API was available with Redis 4, and it was designed to make Redis extensible with new data types and new commands. And our goal was to see if the API can be extended further, so it makes it possible to create much more powerful modules. And as a result of this work, we've had API extensions available as part of Redis 5 and Redis 6. Right now, RedisRaft is still being developed. It's not ready for production and it's not released yet, but we're working towards that. And part of this work involves collaboration with Kyle Kingsbury, also known as Aphir, who will be talking next about how he used Jepsen to test and analyze RedisRaft and the issues he has found. So RedisRaft is not available yet, but it's we're getting there, and we hope to make it publicly available very soon. It will be released under dual AGPL and Redis source available licensing, so we think that will be quite flexible in terms of licensing. And until then, and also after it's released, we will be very keen to get any feedback community. So, thank you.
Okay, I'm going to be talking about the collaboration that Jepsen did with Redis Labs in testing RedisRaft. My name is Kyle Kingsbury. You might know me as Afer from the internet, and my day job, wonderfully enough, is to break databases. I test distributed systems under different sorts of failure conditions and look for what sorts of behaviors arise. My pronouns are he, him. For RedisRaft, we designed a whole new test suite, including a whole new analysis process. We found a bunch of new bugs, 21 in total, and Redis Labs devised a bunch of patches to fix many of those bugs. As a result, things look a lot better. RedisRaft is now much more on track to getting a strict serializable test result. I'm going to tell you a little bit about Jepsen, the testing library that we use, how we designed tests for RedisRaft, what we found, and then we're going to finish up with a discussion of where RedisRaft is going forward. So in order to understand the behavior of a database like RedisRaft, we need to understand what it does for clients. And in fact, we're going to do no instrumentation whatsoever of the actual database. Instead, we have clients perform operations against the database and record only the client perspective. That's going to let us infer, hopefully, whether the database looked safe or not to clients. So we run 5 instances of RedisRaft communicating over an IP network, and each client goes through a simple loop where it generates an operation, say set x to 2 or read the current value of y. It applies that operation to the cluster by making a network request using the Redis protocol, and then it records the result depending on whatever happened. That result will include, say, the result of a read or the result of appending something to a list. And we could terminate with an OK operation, in which case we know it took place. There could be a definite failure and we know it did not take place. Or there could be an indeterminate result. So there could be a timeout or a crash or some other behavior that we don't understand. When that happens, we're going to leave the invocation open for all time, concurrent with every later operation, because it might be the case that that operation could take place at some later time. So all of these clients acting concurrently build up a concurrent history of operations. The client on top here performs a write of 2, which fails, but concurrently the process below it performs a read of 5, which succeeds, and so on and so forth. Now with this history, we can start to ask questions, like, do we ever see a case where some operation performs a write of a value, the write fails, but the value that was written is visible to some successful read later? That would be a case of dirty read. We could look for all kinds of anomalies, and this idea of generating randomized histories and then verifying some abstract property over them, this is a common testing methodology in distributed systems. It's based on ideas from quick check and generative testing. While this is going on, unlike most quick checks, we're going to kill nodes, we're going to introduce partitions and process pauses and all kinds of weird anomalies. And the reason for that is because distributed systems in production are characterized by recurrent partial failure. It's often the case that nodes are doing strange things, they're getting slow, they're getting partitioned. We want to understand what the system does in those cases. So for RedisRaft in particular, the property we want to measure is called linearizability. And that means that every operation appears to take place atomically, in a total order, at some time between invocation and completion. Atomically means that you can never interleave operations, so I can't see half of an operation. I have to see the whole thing executed or none of it. A total order means everyone has to agree on the sequence of events. And that's a tricky property in distributed systems. The real-time property means that we have to be able to see some state or write some state that transpired, or at least appeared to transpire, after we sent the request to the system and before we received a response. Now, Redis also has a transactional model where you can call multi, any number of Redis operations, and then exec or discard. That whole thing gets batched up as a single Raft operation, which is sort of like a transaction. So we're actually looking for a property called strict serializability, which is linearizability applied to transactions. Instead of having single operations, our operations will be composite operations with multiple puts and gets and sets and appends and all kinds of stuff inside them. Any old Redis op. Now, to measure strict serializable systems, traditionally Jepson's used a library called Gnosis, which is based on work by Wing and Gong and also by work at Oxford by Howe. This system works for linearizability and also strict serializability since they're essentially the same property. But it's got a problem. In order to find whether a history is linearizable, Gnosis works by finding every possible sequence of events. So anytime there are 2 or 3 concurrent operations, it looks for every possible order of those operations and says, does that order make sense to me? The problem is that there are 6 possible orders for 3 concurrent operations. And if we have n operations, there are n factorial possible orders to check. And factorial is huge. It's pathologically big. And because when we have crashes, we have to leave operations concurrent indefinitely, it's going to balloon the size of the state space over time. State spaces of 10 to the 35th operations are not uncommon. So for RedisRaft, we introduced, pardon my dog, pardon the neighbors, we introduced a new testing methodology called L, which is a collaboration I've been working on with Peter Alvaro from UC Santa Cruz. In L, we say yes, checking arbitrary data types is an NP-complete problem, but maybe we can solve a limited subproblem of serializability checking or strict serializability checking by maybe choosing one particular data type. So let's look just at lists which can only be appended to, and for every append, we'll make that append unique. So you can only add distinct elements to lists. If I have list 1, 2, I could append 3 and get the list 1, 2, 3. If I see the list 1, 2, 3, and I know that those are the only types of operations in the system, then I can infer a history of that particular object's versions. I know that the current version, 1, 2, 3, descended from a write of 3, which must have appended to a state of 1, 2. And that must have resulted from a state of 1, and that must have resulted from the empty state. I can identify every write and every version in the history. Being able to map back and forth between writes, versions, and transactions means that given a large set of transactions, I can infer a rich language of dependencies between them based on what different transactions read from other transactions, or which transactions overwrote other transaction values, or failed to observe the writes of other transactions. Those 3 classes of dependencies are actually a language developed by Atul Ajia for characterizing serializable, snapshot isolated, and other sorts of transactional systems. And it turns out that in this language, anomalies, transactional problems, are actually characterized by cycles in the graph. Any place there's a dependency cycle, there can't possibly be a total order of events, because if you chose A then B, B also must come before A. So we look for these cycles, and cycle detection is a linear time problem, thanks to Transient algorithm. Once we find a cycle, we know we have a minimal anomaly. So we can detect G0, which is dirty writes, G1A, aborted reads, G1B, intermediate reads, G1C, writes information flow, G single, which is read skew, and G2 item, which is a type of anti-dependency cycle. And we can also detect session and real-time variance, which is enough to get us up to strict serializability. In order to implement this technique with Redis, we need some sort of list data type, and Redis has lists built in. So we use lrange for list read and rpush for list append. To build transactions, we use the multi command. So everything sort of comes out of the box. While this is going on, we introduce network partitions using IP tables. We kill processes using kill-9. We cause pauses in process execution via sig stop and sig continue. We skew clocks in order to identify if there are timing bugs, places where the system's correctness depends on the wall clock. And we also introduce membership changes, so we're adding and removing nodes on the fly from the system. We tested a number of development builds throughout February and came back to do additional tests in April and May. Starting off with 1B3 FBF6, all the versions that are here are going to be git SHAs. We tested using a 5-node Debian cluster running on both LXC in Linux containers and an EC2, both with and without proxying mode. Proxying mode is where RedisRaft nodes, if they're followers, will send their requests over to the leader in order to get a response. If you turn off proxy mode, you can only make requests against one particular node, which believes itself to be a current leader. We found a number of issues in RedisRaft. I'm going to talk about all of them because they're all very exciting. The first bug we found was an infinite loop, and this happened when we made any single request to a node with proxying enabled. Any sort of event, any request would trigger an infinite loop to occur, where the node logs would just balloon over time. This occurred because when a follower received a request, for example, a set operation, it would wrap it in a Raft set operation and send that to the leader. The leader would then replicate it via Raft, broadcasting it to the followers, getting acknowledgement. And then when the operation was committed, it would say, great, let's apply that operation. So follower, go ahead and apply set. The follower says, how do I do a set operation? Well, I need to wrap it in a Raft set operation, and then I can send it to the leader. And the cycle repeats indefinitely. So this caused the cluster to fall over as soon as any request was made. This was fixed in D589 by adding a reentrancy check to make sure that that cycle only happened once. When we tested without proxy mode, we found that RedisRaft appeared to lose all of its data as soon as any failover happened. This occurred because without proxies enabled, followers were supposed to ignore commands, because only leaders are supposed to execute them. So the leader would get a set operation, broadcast it via Raft, it would go into the Raft log, and when it was marked as committed, the follower would say, great, let's apply this set operation. How do I do that? Well, I'm not supposed to do anything, only the leader is, so I'm going to ignore the operation. As a result, data was replicated in the log, but not in the actual state machine. As soon as a failover occurred, you get a completely fresh state with none of your writes. This was fixed in D589 as well, by adding the reentrancy check. The next bug we encountered was a case of SplitBrain, which led to lost updates and other anomalous behavior. And this was a bug involving membership changes. When you change membership in Raft, you enter a mode called joint consensus, where you're supposed to operate with agreement from both the old and the new set of nodes concurrently. They both have to sign off, or a majority of both have to sign off in order to make progress. However, in RedisRaft, you could tell a leader to remove a node, and it would execute the removal immediately without checking with anybody else to see if it was okay. So you could say, forget about those other nodes. Just go ahead. You're the only one left. And the leader would happily go on to execute those operations independently. You could do as many writes as you like, and nobody else would have to sign off on them. As a result, you could turn a 5-node cluster into 5 separate 1-node clusters, each one of which with its own tiny universe. This occurred because there was a set of log operations in the underlying Raft library, which were supposed to be considered configuration changes and gated by that majority process. The Raft log type remove node message type was left out of that set by accident. Adding it back in ADA 0 fixed the issue, at least in part. Some other fixes happened in issue 28. Bug 18 involved transient empty reads on startup. So you'd be running along, executing appends, say adding 3 to a list, and maybe you could read that 3 back from the end of the list. You kill a node and restart it. And then the very next read you performed against that node would observe an empty state, a list with nothing in it. Where did the writes go? Well, they weren't gone entirely. They came back after a few seconds. This was because the underlying Raft library didn't issue a no-op log entry when a new leader was elected. And that's something that I've seen in a few different Raft implementations. It's a subtle part of the protocol. Adding that check back in DFD9 fixed this issue. It was already addressed in the upstream library, and all the RedisRaft authors had to do was pull the new version. Bug 19 involves stale reads in healthy clusters. So even without faults, we found that nodes would occasionally appear to go backwards in time. You could see the state 1, 2, then 1, 2, 3, and then 1, 2 again, which suggests that maybe some data was lost, except that the full value came back later. So we know those writes weren't actually gone. We just saw some value from a few seconds ago. This was the same bug as 18, and it occurred because elections in Raft occur even in healthy clusters, anytime there's a transient timeout or interruption. This was also fixed in DFD9. We had a persistent issue throughout our early testing in which nodes would decide that there was no leader, even in a healthy, fully connected cluster. They would all kind of look at each other and go, are you the leader? Are you the leader? And nobody could make any progress. This would last for hundreds of seconds. So you'd be going along and you just, no leader, no leader, no leader. And this actually turned out to mask some bugs later. This was caused by a connection handling issue in RedisRaft, which after an election could cause connections to stall. There was a head of line blocking problem, as it turned out. And those stalls could last maybe indefinitely. So you'd end up with nodes that didn't figure out that they were supposed to make progress. This was caused by aggressive default timeouts as well. So because of this bug, and because timeouts were very short, we had frequent elections, and each election could have a chance to put a connection between nodes into some sort of stuck state. That was fixed in more recent builds. Number 23 involved aborted reads with no leader. So you'd execute a write of some value, say appending 3 to a list, and then you'd get back a no leader error code, which is supposed to mean that the operation did not take place because there was no leader to execute it. However, later LRange requests would still observe the value that you wrote, which suggests that you had read some aborted state. This was addressed by a whole suite of protocol level fixes applied in E657. Bug 25 occurred in transactional operation when we tried to discard things. We found that discarded transactions weren't always entirely thrown away. Sometimes some of the operations were squirreled away and showed up later for strange reasons. So you try to execute a pair of operations, say a set and an rpush, inside of a transaction. So you call multi, set, rpush, and then exec to commit. But in case any problem occurred during this process, you might wrap that set of operations in a try-catch. And if any error occurs, you would call discard in the connection to throw away that transient connection state. That way, when you did more multi-operations later, they would start off with a fresh slate. Mostly. Sometimes the discard operation would fail, and those set and push operations would be saved for later and appear in later reads. So at some later time, you might start a multi-exec and make, say, a single get operation in it. And what would actually get executed would be a set, an rpush, and then a get. So you could have some strange state get returned to you that you didn't plan on executing, as well as mystery side effects. This happened because the discard operation wasn't executed locally, but went through the Raft log like any other operation. This makes sense because the state machine in Raft, inside of Raft, the Redis state machine could execute the discard operation just fine, but sending the discard operation through the log could fail, which would leave you in this kind of awkward state where you couldn't necessarily back out of your temporary transaction. So this would leave the connection in a multi-state. This was fixed in F4BB by moving the state machine for exec and discard into the local node. So now the local node buffers your changes in memory before applying them. Only when you call exec does it submit anything to Raft. Bug 26 was an error involving what looked like crossed wires. With network partitions and process crashes, RedisRaft could send responses to entirely incorrect clients. So you'd make a request like, get the current value of 2, and you'd get back a transactional response for 3 writes, which made no sense. I thought for sure that there was a client error or something had gone wrong inside of Jepsen, but sure enough, this was actually a real bug. If you were lucky, you get back an object of the wrong type, and you get a type error. If you're unlucky, the response message you get would be of a compatible type, at least for the values you cared about reading. And then you could get silent data corruption, because the values you were reading had nothing to do with the actual requests you made. This occurred because the proxy command handler inside of RedisRaft basically had a typo. It used the RedisRaft context rather than the request context object. So it sent responses to the wrong place. Leaders also were rebundling multi-transactions, and there was some error handling around asynchronous context cleanups that had to be addressed. So all of these fixes are packaged together in E657. Bug 28 involved additional cases of SplitBrain and lost updates. This occurred with membership changes, always fraught with peril, and if crashes occurred during that time, you could end up in weird split-brain states where some parts of the history would diverge. So one node would think the history was 125, and another node would think it was 1345. This was due to a bug in the underlying Raft library involving node removal. The Raft library assumed that nodes would be demoted and then removed, but nodes were just removed directly, and so that led you to get into these sorts of weird shadow states. It also was exacerbated by a design choice in RedisRaft where nodes were left running when they exited and they still had all their old data files sitting around. And this should be safe because that node that was removed might not know that it was removed and so it shouldn't be expected to shut down. But if you tried to rejoin a node that had been removed, it might have a chance to rejoin with its existing data files and cause chaos. So that was fixed. Both these are fixed in BC95. Bug 30 involved another case of transient empty reads. Nodes which restarted after membership changes could, for a short time, show you empty data sets instead of the actual data. This bug was really rare. We had to test for hours and hours to find this one. It involved a bug in the log loading process. So when RedisRaft starts up, it looks at the log on disk to decide what state it should be in, and it tries to replay operations to get to a good state. And when it's trying to decide which operations in the log are committed, it needs to know what the cluster membership was at that time. So when it's replaying the cluster membership state, it accidentally used the set of all nodes rather than just the voting nodes in order to determine the committed state, and that resulted in entries being inappropriately considered uncommitted. It could also treat former members of the cluster as if they were still active. It could treat former instances of the same node as if they were still active, which meant it could send itself messages and maybe get responses back. All kinds of weird things could happen. So this was fixed in 7.3 AD. We found another case of SplitBrain. And this one just happened today, actually. It's where you could have one history that diverges at the end. So you have one node that thinks it's 1, 2, 3, 4. One node thinks it's 1, 2, 3, 5. This turned out to be due to a bug in the snapshot loading process. Sorry, this is a bug I found last week. There's a different SplitBrain today. But again, the snapshot loading process, which caused the in-memory state to be fine. Nodes could still execute things correctly. But if you took a snapshot from the thing that you loaded, it would be missing some of the nodes because the snapshot loading process didn't actually call the right completion methods. That was fixed in 2D1C. But in 2D1C, we found an assortment of other issues, a collection of crashes. We found 8 different crashes in recent builds: 42, 43, 48, 49, 50, 51, 53, and 54. These crashes happen in response to network partitions, pauses, crashes, membership changes. Some of them just required a pause or just required a crash or partition. Others required a combination of faults. Most of them are either a seg fault or an assertion error. Some of these assertion errors point to invariant violations in the Raft library, which are a little bit concerning. But the good news is that most of them were not associated with any sort of observable anomalies. So we didn't typically see any sort of write loss or weird results of reads in these cases. So RedisRaft is going to be addressing those. Bug 52 involved dueling histories. And this is a strange one. It's another type of SplitBrain where you might read the value as 1, 2, then 1, 2, 3. You're appending objects to this list. Everything is great. And then maybe seconds later, a value that you appended might disappear from the history. So you have 1, 3, 4 and no copy of 2. Or maybe the node goes back in time and inserts duplicate operations. So you get 1, 2, 2, 3 or 1, 2, 3, 2, 3. All sorts of strange things can happen. And nodes would fight back and forth over what the current value was. This points to some sort of Raft invariant violation, but it's not clear what exactly. We just found this one recently. And it involves process kills. So crashes alone are enough to trigger this issue. Redis Labs is going to be investigating that as well. So, to recap, we found 8 crashes. One case of spurious unavailability where nodes would go down for apparently no reason. 3 cases of stale reads. 1 aborted read. 5 cases of data loss or duplication. 1 infinite loop. And 2 cases of logical data corruption. In short, this is a bit of a tire fire. But that's okay. We expect things to be tire fires when they're early in development, and that's exactly what RedisRaft is. The first commit to this project was in early 2018. Redis Labs started working on productionizing it in mid-2019, and we began our testing in 2020. Here we are in May. Things are still under active development, and we expect there to be lots of bugs at this phase. And none of these bugs have any production impact because there are 0 users of RedisRaft. It hasn't been announced yet. So, this is where we want to be. Redis Labs, moving forward, is going to be addressing all the bugs that we found. So we're still finding new bugs. Today I found 4 more. There's still 1 safety violation that we know of, and some of the crashes look like they could be invariant violations too. So once those are fixed, we might find even more things. There's more to do, but that's okay. This is what we want at this phase. I should emphasize that Jepsen cannot prove RedisRaft is correct. So our failure to observe phenomena doesn't mean this phenomena cannot possibly happen. It just means that our test wasn't rigorous enough or wasn't using the right types of operations to find those errors. I also should emphasize that we didn't test Redis Sentinel, Cluster, Active-Active georeplication, or any of those flavors in Redis Enterprise. This is important because those are the versions of Redis replication you can use today. Sentinel and Cluster, which are used inside of Enterprise, were designed for a different sort of world without network partitions, and as a result, they do interesting things and lose updates when partitions or other failures can occur. Active-Active georeplication is based on CRDTs and should be partition tolerant, but I haven't looked at it. Redis Enterprise is of particular note because the Redis Enterprise webpage currently says or said as of last week, that Redis Enterprise offers full ACID compliance with support for multi-exec, wait, discard, and watch commands. And that sounds great. Who wants full ACID? Everybody wants full ACID. But the problem is that you only get that full ACID support if the system's not replicated. So you can't have multiple copies of your data. You also have to use an append-only file that fsyncs in every write, and you cannot roll back when transactions fail. So the question is, how many users are running this configuration? And did any users who are using replication assume they had ACID guarantees? They could be forgiven for thinking so, because immediately prior on the Redis Enterprise landing page is a bunch of advertising about high availability with instant failover protection and adding new nodes and replication. So these two features can't be used together. You can have ACID or you can have high availability, but not both at the same time. If you're running a replicated Redis Enterprise cluster, bottom line, you should probably not expect anything like ACID, probably not serializability, probably not even prevention of write loss. So expect your data to go missing and you won't be disappointed. But that's okay. That's what databases are for. So put your data into some database and then replicate it continuously into Redis. And then you can take advantage of all the wonderful things Redis does, like having a really fast cache and lots of cool data structures and being a good scratch pad for different clients. So you get a best of both worlds approach, but keep the stuff that's really important in some other database. This won't have to be the case forever. RedisRaft, if the Raft implementation then solidifies, and there's no reason it shouldn't, should solve these problems. It should give you strict serializability. It should give you replicated durability. So at this point, it's just a matter of hammering out all the bugs. And that's going to be a long and tricky process. Redis Labs is aiming for release in 2021. And they've also changed the web page for Redis Enterprise now. So there's a little link that says more information about these ACID guarantees is available here. And there's a blog post that talks about what you have to do to get ACID, which is don't replicate. Redis Labs has a bunch of development work to do, and we'll probably be coming back to do even more Jepsen testing going forward. No, not for chewing. And Redis Labs is going to be targeting GA in 2021. In the meantime, I'd like to look at developing more workloads. Our tests are based on list append only, so we didn't look at registers, sets, counters, channels, that sort of thing. So it would be interesting to look at those. The reason we haven't tested other types of operations is because, at least in theory, all of these are going through the same concurrency control mechanism. And once they're applied to the Raft log, as long as the Raft implementation is solid, applying them in the single-threaded in-memory Redis state machine should be straightforward. So I expect all of them to work the same, but I'm not necessarily sure. It would also be nice to look at other faults. For example, file system corruption, the loss of un-fsynced writes. We've been seeing a lot of issues with taking snapshots and replaying snapshots and logs, so maybe some more aggressive poking at the file system would be in order. I'd also like to test Sentinel, Cluster, and the CRDT implementation. I did Sentinel testing a few years ago, but I haven't come back, and I understand they've made a few improvements which don't eliminate data loss, but might substantially reduce it. So it'd be nice to get a qualitative picture of how often these things lose data, what types of anomalies you can expect, and are there certain configurations or use cases where it makes more sense. This work is funded by Redis Labs, and I'd like to say thank you to them for all of their technical and financial support. I also want to say thank you to all of you for taking the time to watch this talk. I hope that you've found it entertaining, you've learned lots of things, and you're excited about having a strict serializable Redis in the golden future to come. If you want to read more about this work, our report is not live yet, but we're aiming for release June 30th. It will be available at jepsen.io. So thank you all for your time, and I hope you're taking good care of yourselves through the uncertain time we're living in.